All right. All right. Now I think we have sound. The sound was had come unplugged there. All right. So we'll start over with what we're talking about today is stress concentrations. And I've already pulled up a chart. You've looked at it, but maybe you don't know what it's talking about. So the idea here is that what we've been calculating is the average stress in a bar or a plate or a bracket or whatever it is, a rod, a beam, all these different elements that we've been looking at. When we calculate the stress in there with sigma equals force over area, or one of those equations that we've used, that calculation gives us an average stress. But whenever you have some sort of transition from a large area, like maybe this little picture here, it's got a large end and a small end. So there's a transition governed by this little, what's called a fillet here between the two. The transition there, I've got a sharp corner somewhere, I've got a hole punched in something. Anytime I change the geometry then of the part that I'm talking about, then I create what's called a stress riser. And the more severe that change is, like a really sharp corner or something like that, then the more severe that stress riser becomes, and it creates a higher and higher local stress. So the stress right around that riser will be higher than the number we've been calculating. And what I was saying is there's two main ways that we have dealt with that. One of them is these charts that we look at. So here's a chart for a plate that has a hole punched in it, a tab. Here's a torsional setup. Here's a bending setup, also with a tab looking plate. Here's a bending setup for a notch. So there's a whole bunch of these charts. These are the ones that we're going to look at, but you could have many more. And each one describes a particular loading situation and some geometry. So for instance, let's just look at this one. The plate, you have how wide is the plate, how big is the hole in the plate, what's the force, so P. We're assuming that the hole here is centered in this plate. And if all that's true, then we can use one of these lines, one of these traces on the graph to calculate what's called K. K is over here on the y-axis, and K is the stress concentration factor. And so what it'll do is we can multiply the stress we normally calculate, force over area or whatever, by K, and that will tell us how much to expect an increase in stress near that change. So in this case, like near the hole. So that's how it's been done for a long time. But there's also finite element analysis, SolidWorks, Fusion 360, programs like that that can simulate how a part that you've designed is going to respond to stress or to respond to force. And it will show you like a stress gradient. What kind of stresses can you expect to see in this part? And it won't just show you the average stress force over area. So it's a pretty simple process. For the exam, there'll probably be one of these on the exam. For the exam, we're going to do by hand. There might possibly be a content question about stress concentration factors in general. Maybe there's just a question about it, but or maybe about finite element analysis, which we'll look at later. That's what we did in Lab 1 and Lab 2. We'll actually do a simpler thing now to go along with this. But I think the easiest way to do this is to solve one by hand using one of these charts, and then set up the same thing in SolidWorks. We'll use SolidWorks for this, and see how close the two agree. So let's go over here. And set up some type of let's do a situation that'll match the tab looking thing. So one side's bigger than the other side. So we'll do something like that. So we'll do this. Well, let's try to get a little straighter than that. Now here, this transition area from the large side to the thin side, or the more narrow side, That's going to be done a couple of different ways. One way is we could just have a corner. Um, in general, having sharp corners is going to be bad design practice, because the sharper the corner, the more severe that stress riser is going to be. And you're going to get, well, let's look at the little charts. Where would they be? They were over here, I think. Look how the charts, when you get on the left hand side, all these traces just kind of start taking off into these really large numbers. So the it almost becomes vertical for these traces the farther left you go, which is controlled by the radius, or the radius of this fillet right here. So the smaller that fillet is compared to the size of your part, then the higher and higher the stress concentration is going to be, and that's generally bad. So you normally don't want a sharp corner there. And also, it's kind of hard to make a sharp corner sometimes with CNC type of procedures, or even like additive processes. Sharp corners can be hard. So in general, sharp corners are not your friend unless you're making some kind of tooling for a die or something like that, where you're trying to shear something, and that's a little bit different process. All right, so we're going to have a rounded transition between the left-hand side and the right-hand side. Oops, the touch. There we go. So something like that. Something like that. So this little feature is called a fillet. And yes, it is spelled like fillet, but it is a fillet, like you're filling in the gap between these two pieces. But it's a fillet. And what I've drawn is pretty extreme on the rounded side. They do approach a sharper corner than what I've drawn here typically, but there will be some transition there. And we want it to be generous enough, or like smooth enough, that it doesn't create super high stress concentrations. So let's put, I don't know what dimensions we need on here, but actually let's not put that one there. Let's put that one over here. Let's say that this tab is half an inch. And this part, we'll do it this way. These are not the really right ways to put the dimensions on here, but I'm trying to leave room for the force. So this one, if that's half an inch, then this is 1.5 inches. And then let's make our radius of our fillet here. Let's make that not too big, even though I've kind of drawn it big. Let's make it 0.05 inches. And that'll be the radius there. Let's put a force on here. So we'll have an axial force, and let's just say that this is a, I don't know, 250 pounds. And then we'll need a matching 250 pounds over here. How did I turn that off? Well, we'll see. We need the thickness of this plate, so let's just say the thickness is 1/10 of an inch. No, let's do 1/8 of an inch, so 0.125. All right. Now what we would do before, the first third of the class, we did problems like this, is we would calculate a normal stress, or an axial stress, and we would say sigma equals F over A. And then we would go in to our part, look where, just eyeball, where is the larger stress going to be? And we would say that, well, the larger stress is going to be wherever A is smallest and F is largest. F is the same anywhere in this loading configuration that I've shown. But A is, it's smaller if I go over here somewhere. So we draw the little free body diagram of our part here. So maybe something like this. And we have our external force, 250 pounds. For this little piece to be in equilibrium, I need a matching 250 pound internal force. So hopefully by now you don't really have to draw these particular type of free body diagrams, but I still draw them just because it just makes it even more clear. Now in an exam where you're kind of under a time constraint, maybe you don't draw something that it's obvious, but when we're doing this, it makes it more clear. And then we go in and calculate stress. All right, so stress sigma equals the internal force, 250 pounds, divided by the cross-sectional area, which is going to be the cross-sectional area kind of where I cut it open here, which I said, it kind of scrolled off the top here, but I said that was 1/2 inch wide and 1/8 of an inch thick. So the area would be 0.5 inches by 0.125 inches. And we get a number. Got to find my calculator to see what the number is. Let's see. 250 divided by 0.5 divided by 0.125. 4,000. Okay. 4,000, those units would be PSI, pounds per square inch, or 4 KSI, 4,000 pounds per square inch, if we did KSI. So that's not too bad. If this is a steel of some kind, then our yield strength is like 30-something thousand, 36,000 PSI. We're way under that. So we have definitely, I would assume, made our factor of safety. But if we go back up here, what we calculated, if I can try and draw the stress profile, is, well, for one thing, the way that I've shown this picture is I've applied a whole bunch of force at one little point right here. So normally these point loads that we draw, like the single arrows, they're not really realistic. Most everything is spread out over some amount of area, and they're not like infinitely small, because that would create a really high stress there. But this would create a really high stress concentration. So I'm trying to draw here the higher stress at that point load. But what we calculated is at some point it kind of evens out. And so we kind of calculated the stress here, sigma average. And so that's normal. That's what we've been doing. But now we've got this fillet where we have a small area going to a larger area, or vice versa, depending on which way you're looking at it. And you might have somewhere, I don't think I've ever done it in this class, this course this summer, but you might have seen something about like stress flow or something like that, flow lines or stress lines. And they're sort of like if you imagine airflow lines in a wind tunnel. So, you know how the stress is going to flow from here. I'm making it flow this way just to make it seem more like a fluid, I guess. And you know, it's averaged out kind of in the middle of the larger section, and it would be doing the same thing going from the other section. But now it's got to pinch down, you know, to make it all into this more narrow section. And so these areas here and here have that stress compressed into a smaller area, and it will create a stress riser. So that's what we're going to calculate now is, well, how much can I expect the average stress to be multiplied by around this stress riser? So we calculate the average stress like we just did, and then we are going to calculate the stress concentration factor and multiply the average stress by this number K, and that should be somewhere near what we would expect the higher stress at this transition to be. So for K, we'll need our charts. So that's going to be over here. We have this situation right here, which is also the same as a plate with a hole in the middle of it. So it's the same set of graphs, although the circular hole just has one line. The top line is the circular hole. These other 4 lines are for the tab. So it's, first of all, we need to know what line we're on. So we're not on the circular hole line. These other lines are controlled by uppercase D divided by lowercase d. So looking at our picture, uppercase D is the width of the large part, lowercase is the width of the small part. So for us, that is 1.5 divided by 0.5, so 3, right? So let's see if there is a line for 3. There's not. There's a line for 2, so I probably should have made our lines match up. But so we're going to be off of our chart somewhere. There are ways now on homework and exams and things like that. You land on one of these lines. You don't have to worry about it. But we actually landed off of one of these lines. But if you notice that the lines are getting closer and closer together, the larger this ratio gets. So the 3 line is not going to be very far above the 2.0 line. So we'll just go estimate. We won't get too exact into extrapolating where exactly 3 is going to be. We're just going to estimate it's slightly above the 2 line. So we'll do that. So we're going to use this little curve here. Now we need to know our x-axis, which says radius of the fillet divided by lowercase d, which was the tab here. So for us, well, let's write our things down. D over D equals 3. I probably would be better off copying this and putting it on our OneNote sheet so that we don't have to flip back and forth. So there's that, and then we will put it somewhere over here. There we go. All right, so we know we're on this line. Well, we're not on that line, we're slightly above that line. So we're somewhere above it. And there are ways that we can extrapolate based on the other 4 lines and figure out where exactly we are. And again, like I said, on exams and homework, you're going to be on one of the lines. You don't have to worry about that. But we're just going to kind of eyeball it. So our other factor is, I cut it off. This bottom part is R over D. So R for us is the radius of our fillet, I said, at 0.05 inches. And D is 0.5 inches. So that gives us 0.05 divided by 0.5, 0.1, no units. So that is actually on here. It's at the very end of our line, right? So there's the 0.1. So I'm going to say that if we are on the right above the 2.0 line and at 0.1, then we're right here where K equals 2.2. So what we do with that is we take our stress that we just calculated, sigma average equals, we said it was 4,000 psi, and we say that our sigma max, or our multiplied stress, maximum stress that we can expect around the fillet, equals K times the average sigma. So that's 2.2 times 4,000 psi. So we can expect to have 2.2 times 4,000, 8,800 psi. We're still safe if this is steel. Steel doesn't have a yield strength until in the 30,000s of psi. So we have a smaller margin of error to get there, but we still have plenty of margin of error. And that's how you use these charts. It's really straightforward. Like I said, we did do a little bit of eyeball guessing since we didn't land on one of these exact lines. But on the exams and tests, you don't have to deal with that part. You would be on one of the lines. You just have to read the chart. Now, let's do the same thing, but in SolidWorks. So I think I put SolidWorks over here. No, let me get SolidWorks showing up. There it is. All right. So that we've had a blank space here for a new part. So first thing, we have to model the part. So that's going to be a sketch, and we will create it on just the front plane is fine, and it is something like this. We'll have to put our dimensions in. Oh, it's going to have some crazy issues here. That'll be okay. That one I can't really tell where. Alright, so let's fix some of this stuff here. Alright, so this line needs to be horizontal for one thing. There we go. And let's put some dimensions. I said this was I am in IPS down at the bottom. Can you? No, it's off your screen. But at the very bottom of the screen, let me see if I can get it to show up for you, so you can see all of the. There it comes. All right. So down at the very bottom down here, it says IPS. That means inch, pound, and second. So I made this 1.5 inches. I don't think I even set this dimension. Let's go look at our, it wasn't relevant to calculating what we were calculating, but let's kind of flip over there and see kind of what it looked like. It looks like it's 1 inch, so we'll put 1 inch there. And same here, we didn't constrain those, so they're not moving around. This guy, well, this one, we made at 1/2 inch, which it's really close to. Also, same thing here. I didn't set a length on this in our original picture. It looks like it's 1, 2, 3, 4, 2 inches long. And that moved that one. We do need this to be centered. So let's just set this dimension at 0.5. And that should make that one also 0.5. Let's set our fillets. So that fillet, I made them 0.05 inches, I believe. Let me check. Yes. And I want one there too. So now you can kind of get an idea for the actual scale of those fillets. They're actually really quite small. Now I still have a couple of unconstrained lines here, so technically we should go in and fix that. But I think we're going to be okay. Okay, so I'll finish out the sketch. Oh, and I made it an 1/8 of an inch thick once it decides to wake up here. And so let's extrude this guy 0.125 inches. Call that good. Now for our simulation to work, I'm going to need a material on here. When we were talking about it in by hand version, I kept referring to steel, so let's just do a generic steel. That won't really affect the stress calculations, but it can affect if I allow it to like deform, or if I have it plot anything like factor of safety, things like that, it'll affect those. So we'll just apply a material not specified. Let's switch that to plain carbon steel. That'll be a good. Oh, you can't see that. So what I did, it's not showing up here. I did right click. Actually, let's look at the screen instead so you can see. There we go. I right clicked on material, and I'm going to do plain carbon steel. And you see a slight color change indicating that it's got a material applied to it. It would not be a horrible idea to save things, so let's save it. Let's just put it in its own little folder. Actually, let's put, well, that's fine. It'll be in documents, that's fine. I want to put it in its own folder because when I run the simulation, that's going to generate several other files that I don't want scattered around all over the desktop. So that's why I wanted it in its own folder. All right, so we've got a part, and now we need to do add-ins simulation. Now the simulation we're going to do here is just a static simulation. None of the linear elastic kind of, which is just a load it up and look at the stress. So we could do that on just the premium. I am going to load up simulation premium just because, but you could do this just on the premium version. So it's loading. Looks like we can make our screen a little bigger now. Let's see. There we go. All right, so SolidWorks, here's our simulation tab, new study. We're going to do a static study. So that's the default option when you only have the SolidWorks simulation and not premium simulation, or SolidWorks premium and not premium simulation. So we'll do static. This one would be okay for a 2D simplification, but it's not going to be such a computationally intensive model that we really need to simplify it. We also have symmetry here, where we could create a plane of symmetry and solve this one. Those things are useful when you have much more complex models, but on something this simple, it's almost more trouble to create the simplification than it is to just run the study. So I'm not going to do any of those. So it wasn't 100% clear over here. Why can we not get to? There we go. Wasn't 100% clear over here how things were mounted anywhere, but what I did have was I had a 250-pound force that was applied on one end, and I had a matching 250-pound force on the other end. What I think of when I wrote this, or not wrote this, but drew this, is that this left side would be held in place somewhere, and the force is applied to this right side. So to simulate that in our SolidWorks model, we will do a fixed geometry, and we will fix the whole plane back here. So that whole thing will just be held stationary. And then we'll apply a force over here. So we're going to apply a force on this. Now I want it to go the other way, so let's reverse the direction. And let's use English units because I've had it in 250 pounds. And we'll now look at another difference here is that this force is going to be spread over this entire face, where in the OneNote, or well, I was in OneNote, in this drawing I showed it as a point load. That is a different loading scenario in the real world, loading the 250-pound force on the face of it versus loading 250 pounds on a point of it. Those are different things in the real world, and in the simulation they would be different things. So if I really needed to model the 250 pounds being applied to a small area, then I would need to go over somewhere here and create a small area to apply that force to, because that will make this behave differently. I'm not particularly interested in what's going on over here. I want to know what's going on at the fillet. So I'm okay with this being the way we load it. So now we've got a material. So you can check, it's got a little check mark, and it's really small. I don't know if you, I wish I had a way to magnify that. But there's a little check mark over here, and it says plain carbon steel. We've got that. We have a fixture that is constraining us in 3 directions. So we're fully constrained. And then we've got an external load. Take very long at all. It's done. So take very long at all. It's done. So now it's giving me over here von Mises stress in pascals. So let's change that up. I'm okay with it giving me von Mises stress. Von Mises stress is a way to combine our 3 principal stresses, X, Y, Z principal stresses, whatever direction they might be, and psi, to better compare with the numbers we had, or KSI. Okay. The other thing you usually want to, some things you'll note, let's see if I can pause it, or can I move through it frame by frame? No. Thought I could, but you'll see this top surface up here and the bottom one down here kind of concave in. So that is not in my by hand calculation at all. So Poisson's ratio of, I made it is located, that transition between the larger area and the smaller area. And that is, you know, these stress lines trying to all flow in a tighter space. So we at least have a simulation that looks like what we expected it to look like. Now let's see if we're anywhere near this number. I haven't checked that yet. Actually, we're not far. So here's our von Mises stress. It is maxing out at 9,500 psi. And that's not surprising that it's higher, because typically, let's see if I can close this guy out, and can we show our mesh? So yeah, it's kind of hard to see on here. I don't know if I have a way to make it brighter or not. Let's see, settings, mesh. Yeah, let's edit the mesh color to make it, well, that didn't change anything. No. Oh, I wanted you to be able to see the mesh better. I think you can see it. It's just very hard to see. But see how I've got these points here, and I don't have very many elements. So each one of these lines is an edge of an element for the finite element method. And I don't have very many of them in here. So that will generally lead to some unrealistically high, sometimes they're even way higher than this calculation is going to show you, values in a simulation. So usually when you're looking at your highest stresses here in a finite element simulation, unless you have gone through a long process, a tedious process of really optimizing your mesh, then that number is probably unrealistically high and being controlled by some little singularity type thing, some point on this mesh. And so I typically kind of ignore the highest stresses that are shown on one of these type simulations and look around there. So, what am I getting, kind of around somewhere here? And yeah, I've got some reds deeper into the model. Again, I don't have that many elements in here. There's like one element controlling that whole curve there, from there to there. So I don't have that many elements to work with. But those numbers are in the range of what I expect. And even the very peak number is not that far off. It's the same order of magnitude. So I'm relatively confident that we're doing the right process, both by hand, and we could probably do a better job on the finite element part, but we're accurate. We could go in here and go to our mesh and remesh the thing and try to get, one thing we could do is we could just, have more elements, making it a finer mesh, meaning they're smaller. So that's one thing we could do. What else could we easily do? Let's see if there's we could kind of control some of the element sizes. There's a curvature based mesh. Since we're interested in the curve here, we could do that. So the minimum number of elements in a circle is 8. So since this is a piece of a circle, we could just bump that up. I think these numbers are also controlled. Yeah, they're also controlled. Actually, the minimum number for the circle is not. So we could bump that up to a larger number. Let's just double it. Let's just double it. And I'm not that interested in the stress. And let me let it catch up. It is a little behind. All right, so now we're caught up. It looks like we caught up right at this screen. So there was a little internet issue. So, but around this curve, where I'm more interested in what's going on with the fillet, I have smaller elements. So we controlled that by that curvature, wanting more elements in a circle, which this fillet is a piece of a circle. So let's run that and see what we get. So let's, well, actually the run the studies up here. It'll take slightly longer, but last time it took like a few seconds. So in here it did some more. Now I get a little bit, you know, there's a larger red area, and it's, you know, 10,000 psi now. And again, I'm still of the, so nodes are the vertices for the points here, and they're all lined up in a line right there. That's probably going to give me some issues. And I could still have way more elements in this transition area, but you know, the other numbers around here are in the 8,000 range, and even 10,000 is not that far from 8,800. So I'm thinking that we're accurate with both by hand and our finite element model. Neither one are 100% correct on, you know, which one do you do. On an I keep having some internet issues. I mean, it bounces back and forth between having, I guess we're having internet spikes of some sort. We're about done though, so we're about finished with our talk. So this number just gives you a single number, whereas the finite element gives you, you know, more of a picture of what's going on in the area of interest. You do have the issues with, you know, getting your mesh done better. In general though, if you are not a finite element expert, then the default settings here will give you a good enough first take to just see if things are going the right direction. One thing you can do is you can take a feature somewhere, not necessarily just grabbing the highest stress on your chart here, but take a feature somewhere, run several different meshes. So you could just, you know, have a coarse mesh, you know, a kind of medium, a little higher, and fine mesh. And then wherever that feature is, find the stress, interrogate your model, your results, your simulation, and find the stress of that feature as you increase the number of elements. And what you want to see is that that stress that you're calculating or finding from your simulation is converging to the same number. So it could be that it's, you know, every one of them coarse to fine gives you the same number. That doesn't necessarily mean it's a correct model, but it at least means that it looks like it's converging to a stable model. What you don't want to see is, you know, you plot the stresses that you're calculating, and either the more elements you keep adding, it gets more out of control. It explodes, you know, it's a exponential curve or something like that. You don't want to see that, because that does not give you a good sense for your model. It means that you probably need to go in and you've got some kind of singularity that's developing in your mesh, something like that, that's giving you. But what you will do is you will do a by hand. So I'm going to exit out of here. I guess I have to close the simulation first. So we'll close this guy. I don't need to save it. You will have to do one of these type, not necessarily the plate with a hole or this chart, but a by hand calculation for stress concentration. That's usually on exam 3. But you have several of these charts that you might end up using. There's one for torsion. There's one for bending. They all work the same way. There's a picture that has a set of variables on it. You use those variables to determine the x-axis location and which trace you're going to be on in the chart. And then you calculate the stress like you normally would with the average stress equations we've used all quarter. And then you multiply by whatever value you get for K. And that is the maximum stress you should expect in that situation. On the wrong one. But it will still be relevant. So here's what, and this actually says 2019. So, but the outline is basically the same. Maybe not the same order, like they won't occur in this order necessarily. But the questions will cover these topics. So you'll have some number of content questions. And I've also, not all of these are 6 points. I have changed to where there are a little bit fewer questions, and some of them count a little more than others. But the general idea is the same, and the topics are the same. So you'll have content questions. There could be some question about finite element method, but no calculations or doing finite element method. There might be a question about stress concentrations, and there will be, at least one calculation for stress concentrations. But then notice that a lot of these, what I think of are the fundamental level ones, are actually going all the way back to the beginning of the quarter. You've got axial stress in here, 2D concurrent force systems are in here, a centroid, so it's the stuff that we've done. And then you've got some new material, a couple of questions on pressure vessels, torsion, and then stress concentration factors. And then there's, I'll have to check to be sure. I don't know that there's actually a beam deflection question on there anymore. Let me see if there's a way I can check that. Let me go over here and check that, because I may have decided not to ask you about beam deflection. Let's see, because those can be lengthy or either really simple. So I'm not sure what I decided. Let me check what I put in there. Let's see. Let's see. I did not put a beam deflection in there. Oh, no, I did. But it's just not one of the really harder ones. It's a more simple beam deflection. So there is a beam deflection question, but it's not one of the harder questions on the test. It's more like a fundamental question. All right. That should do it. There on Monday, we'll do just like we normally would for any other exam, except that you will, if you choose to retake a 1 or 2, then you'll log into Moodle, and I will do a 12 o'clock and a 7 o'clock option, and we will either you will take exam 1 retake or exam 2 retake. You can't do both of them. You can't start one and then decide to do the other one. Once you start one, that you have to finish it, because it will, that whatever you make on it is going to replace the previous grade. Now, I've not ever had anybody do significantly worse. So there might be an occasional, not even that many, but an occasional person that makes a point or 2 lower. Just, they basically did not improve. But the biggest gains are usually somebody who had a really hard time with one of the, it was a bad day kind of thing. They were sick, or they just missed the exam, something like that. Those are the biggest improvements. You don't have to take either one. You can be completely happy with the grades that you have for exam 1 and exam 2. They are not the exact same exams. They are different questions, but the same content, covers the same content, and the same style of exam. In general, the average improvement is about 6 points from what you made originally to the new grade. And if you made a really low grade and you know why it wasn't that you didn't know the content, there was an issue of some kind, then that's when you make the 25 and 30 point better grades. So if you want to take one of those retakes, then that's what we do Monday. You don't really have to let me know unless you're doing a proctor, and then I have to set up the password and everything for the proctors. But assuming you're proctoring with me, then just show up. Just know that you can't flip between them, and once you start it, you have to finish it to get the new grade, because I can't let it be where you get halfway through it, decide you're not gonna make any better, and just quit, because no, you got to do the whole thing. So that'll be Monday. Wednesday will be a regular exam like we've done before, and you do need to take that one. That's exam 3. And then Thursday is the last day to get everything turned in. So I think all of the web work is open until then. I think the lab 2 is open until then. The quiz, last quiz 5, I guess, is open until then. And your turning in spot for your project. Make sure that if you're on a group project that you don't each need to turn in something, but make sure your name is on what is turned in, like on the cover page, so that I know who to assign the grades to. All right, let me check the chat to see if there's any. No, the only problem was that I didn't have sound at the beginning, but we fixed that. And we'll be back. Well, actually, this is the last piece of content, so we won't be back with any new content, but we'll be back on Moodle in Zoom for the exams. Let me know if you have any questions.